Hello, this is Miss Salter, and this is the video on Kepler's third law. We had a activity in class that was figuring out the uh, periods of different planets in a solar system far away, uh, using the third planet from their star Gamma as our kind of reference point, and then using Kepler's third law to find the period or the time it took for the other planets to make one revolution around their star. Okay, so we use gammas as a kind of a benchmark. So in our given information, so we were given gamma's information. So our third planet, oops, hold on a second. Okay, so our third planet was Gamma, and Gamma had 2 bits of information we were given. We were given Gamma's period, or T value. That was 1.0 years. So as far as we were concerned, 1 year in this example solar system was 1 trip of Gamma around the sun. Just like with the Earth, 1 year is 1 trip around that Earth makes around our sun. And then Gamma's distance, or R value, orbital radius from their star, was 3.65 times 10 to the 8th kilometers. Or no. Yeah, kilometers. Some videos you might see on the internet will do something a little bit more complicated with this, and not using Kepler's third law, because you should be using astronomical units for Kepler's third law, but because it's a ratio, CK12 thought that it would be fine to use kilometers. We're following that because we're advanced physics, and of course there's always things that we kind of simplify so that we better understand it at our level of physics. So that's why we're using R with a unit value of kilometers. Just a little disclaimer there in case you were looking at some other videos. So now we were given, now the example I'm doing is planet Pi, and so planet Pi is a little further on, and its R value is 2.95 times 10 to the 9th kilometers. And we want to know what its period is, or how many years, gamma years, does it take for Pi to make one revolution around their star. Just like here, we say, oh, well, it takes Mars a certain number of years, I think it's 1.88, to make one revolution around our sun. It's relative to the reference planet we're talking about. So the whole point of this activity was to use Kepler's third law. Kepler's third law is the ratio of the squares of the periods and dealing with the cubes of the distances. So we want to find Pi's period. So when we manipulate Kepler's third law, and you can look up Kepler's third law in the notes, when we manipulate it, we get T1 squared equals R1 cubed times T2 squared over R2 cubed. Now, difference here between exponents and subscripts. The subscript refers to the planet. So in this instance, our number one planet, and let me just put this in a color. So our number one planet is pi. Pi is number one planet. So that means that this period here and this R value here have to do with pi, with that planet. And when we're talking about these two values, that is our gamma planet. Gamma is planet number 2. So therefore, its values plug into this period value and this distance value. Then the exponents tell us what to mathematically do with the numbers we are given. Okay, so that's why the difference here between subscripts and exponents. So when we take, and I'm going to move this up a little bit. So now we're going to plug in our numbers here. So, and actually, let me do this. Yeah, let me do this here. So we want to get, oh, stop that. We want to get over this. So we have our pi value is red, so that would be t squared, and this is pi. And then its radius was going to go on the bottom, 3.65 times 10 to the 8th, and that's cubed. And then we have gamma's values. Oh no, that was not correct. All right, let's go back and fix this. This value is gamma. All right, so gamma's value is on the bottom, 3.65 times 10 to the 8th cubed. And this is why it is always important to make sure that you are doing your work neatly and that you are also writing out some of these steps and not just relying on using your calculator, so that you can find these errors quickly and easily and not waste time trying to figure things out. So 2.95 times 10 to the 9th, that is pi's distance. That's going to be cubed. And then we have to do times gamma's period, which is 1.0 years squared. So when we do this math, we come out with t square, and this is pi's t, square root of, now 1 squared is 1, so we don't have to worry about that. That kind of goes away. But 2.95 times 10 to the 9th cubed, and that means you're going to have to use the caret, like the caret 3. That's the little button on your calculator, so it's going to be 2.95 E9, or 2.95 times 10 to the 9th in parentheses to the 3rd. If you don't do one of these two things in your calculator, you're going to have an awful time trying to get these numbers correct. So in your calculator, you should be doing one of those two things, because we just have the scientific notation and the cubing. So this makes it 2.5672 times 10 to the 28th divided by, and we're going to cube the bottom one, which ends up being 4.8627 times 10 to the 25th, which means that when we divide that, we get 527.9449, and when we take the square root of that, our t period of our little pi planet is 22.98 years. There you go. So that's using Kepler's third law to find the period of a planet. And basically, Kepler's third law is the only one we're having to deal with that where we're using this ratio and we have the same values for both things. We have two distances, one for each planet. We have one period for a planet. We're trying to find the other period. So I hope this is helpful and have a good day.